I will present some work that I did on Kotlin. As Enzo said, I actually heard about Kotlin the first time 3 years ago, but I just started working real on Kotlin basically end of the last year. And so let's talk about the Go. I don't know how many of you have heard of the game of Go. Okay, so someone. And so this talk will be my, let's talk about how to do a computer program play Go. And okay, these are some information if you want to know. And in a sense, well, let's talk about, Go became very famous suddenly, I mean, on the general public last year, because it was the last game where the computer was not able to beat a human. And it was predicted that it will take at least another 20 years for a computer to beat a human. But last year, Google, with the deep learning, managed to beat the world champion. And this was quite big news. At the beginning, nobody was really ready to accept that. And you may wonder why, since chess are basically computer are beating the world chess champion since so many years. But Go is completely different. And this is the world champion, the Go world champion, that when you realize that it's been beaten. And this is how the Go the board, Goban is called, more or less looks like in a play. And so just a very quick introduction. So Google made this product with this software, AlphaGo. And AlphaGo was the first time where basically it was using deep learning to develop a strategy on Go, and then they apply also in several other games. And you can see Crazy Stone is the strongest commercial Go software. And more or less in this area, a bit above 3,000 is the level of the Go world champion. These numbers are more or less a kind of rating. Higher, you are strong. And then Google did the first version that play with a strong professional player, but not exceptional. And then he gained with the Lee, which was like number 3 or 4 of the world. And then he went for the top. And then on top of that, they did another version, AlphaGo 0, that was still stronger than the previous one. And it was also interesting because the old version of AlphaGo were basically learning the deep learning part on using all the human played before. But AlphaGo 0 we started from scratch. So basically they train the net on itself. But we'll talk another bit about deep learning at the end of the talk. Now we'll go a bit more technical on the details and why Go is such a great game, and maybe I play Go. I'm not strong at all, but it's a few years that I play Go. So just a very quick introduction. The rules of the Go, comparing with any other game, are really, really simple. You have the board. Someone have white stones, and the other guy has the black stones. Each turn you put the stones on the board, and that's it. And when you have your stone completely surrounded by the other color stones, the stones go to remove. And okay, now you know all the rules of Go. Okay, there is another rule. You cannot play the same position than before. So there are some cases where basically you hit one stone and then the other can hit back the stone and go back to the previous position. That is forbidden, so you cannot do that. But apart from that, I mean, these are 2 rules. There are no other rules. But the implications are incredible. And so this is the first, just to give you. So basically, if we have this position and someone put the black stone here, the black stone kill all the white stones. But if we have this position, you cannot put the white stone here because it will be automatically dead. And you cannot even put it here for the same reason. So any shape with they are called technically eye. Any shape with the 2 eyes is unkillable. 2 or more than 2 eyes. So it's alive, it's called. Any shape that has only 1 eye is killable. And sometimes those are called false eyes, like this one, because it seems like an eye, but if a white plays on C and B, then it can place on A and kill. It will kill these 3, so this will be only 1 eye, and kill also the other one. So all the strategy of Go is to manage to have a group with 2 or more eyes. And this, but it's not actually a rule. It's something that emerges from the rules. And just for your reference, this, I mean, maybe you want to see it later, but a bit of program that do the Go part. The first one is a client, so it has no logic, but you can use it to play with other guys or play against an engine. Apache is the strongest open source game. Lila Zero is the new one, which is basically based on deep learning, but it's open source, so it's kind of redoing what Google did. And it's really nice. Like I think at the beginning of this year was still weaker than Apache, but probably it will be stronger in the future. And the Crazy Stone is a commercial program, is the strongest. And also Crazy Stone now is switching to deep learning. And we try to explain why. And instead the new Go, it was the old program. So actually there was something that I didn't tell you yet. In the Go, basically, program, there are the old generation, which is a new Go, that is based on a set of rules, more or less like the chess player. Then all the others, like Apache or Crazy Stones, are using a strategy which is called Monte Carlo tree search. And we will see later some code about that. And then that was the current bleeding edge until Google came, and now there is also the deep learning strategy. But deep learning is something that goes on top of Monte Carlo research, so it's not that. Now there is this book in MEAP from Manning that basically explain, is quite a nice book, how to do a kind of AlphaGo yourself. And when I see there was all this example in Python, and I thought, well, come on, Python, we can do better. We can do Kotlin. So what I did basically is taking the code of this book, translated in Kotlin. That was version 1, and then improving on the Kotlin part. And this is one, I think, quite interesting point. So left is Python, right is Kotlin, and it's almost identical. It's quite impressive. I mean, it's not some trivial code. The code is one of the most complicated piece of code. And it has a lot of if-else, and it's really, really, and I mean, so far I was considering Python the easiest and cleanest computer language. But I think Kotlin now is still better because it also has types, so it can really help you. With Python, sometimes it's really difficult to understand which type is expected or something like that. And just to give you an idea, this is the algorithm when you place a stone. So basically, well, first there are some guards that we are in the grid, and the point is actually free, because otherwise, of course, you cannot place a stone. Then basically, it creates some set that we wanted to know on the stone that we put, which are the stones of same color, on the opposite color, and the liberties. The liberties are basically the free place around. When you have a shaping go, basically, each on the border there could be another stones or it can be empty. The empty are called liberties, because when you got no liberties, basically you died usually. So basically, for each neighbor point, assuming okay, this is a bit old version of code. Now it's a bit more. Because this is when I did the conversion. Then if you look at the code in Git now, it's a bit more, not complicated, but it has a more optimization inside. Basically, it check the color and they put in one of the three set liberties, same color, opposite color. Then it create a Go string. Basically, I will look, but the Go string is a set of stones of Go that are on the same, basically they are touching each other. Not in diagonal, but directly. And then if the stone is touching other same color, stones of the same color, basically you have to merge the string. In one, or if you are putting a stone where three strings are almost touching, basically you have to merge three strings. And then once you do this, you have to remove the liberties to the other strings that are around, because now you are putting, so that is not a liberty anymore. And if some of the opposite color has no liberties left, that means that you completely surrounded a string, and you can put those stones away. So this is one of the most complicated piece of code, and it's really impressive. It's very linear, and it's Python and Kotlin are really, really similar. Okay, a bit of lesson learned so far. About the types, the question mark types, sometimes, at least for me at the beginning, also because I had some experience with Groovy, where using the question mark is not such a good idea. It was a bit scary to use the question mark in Kotlin. But then I completely changed the idea. I think a question mark is really, nullable types are really good things. So far, the types are really nullable. If there is a reason why the response can be null, a domain reason, that's completely fine, that's great. If there is no reason, the only reason that you put the question mark is because you have a lazy initialization, stuff like that, that's not good. But instead, the double exclamation mark is very bad. So I think there are no, or maybe very few in some case. Because every time you put a double exclamation mark, you are saying, okay, this type, it can be nullable, but not here. And why not here? That means either there is some abstraction that is missing that you wanted to remove, or there is a kind of not so good coding, because actually it can be null in that point, and you can have problems. But we don't want to have a null pointer exception, so really we should avoid double question mark. Immutability is very nice, it's fantastic, but there are also some performance issues. So if you are in the very, very high performance code, maybe you wanted to verify, because sometimes it's helped the performance, sometimes it's not. So it's something we can maybe look at some code. Algebraic data types, which are the sealed class where you have several instances, are great things. And they can really help both performance and simplify the code. And the premature optimization is the root of evil. So you have to think, it's very good to optimize the algorithm, but before trying to optimize the code, you really have to measure. For example, at the beginning, I tried to put some inlines around, but inlines have absolutely zero impact on performance. Unless there are some specific, like lambda parameter and stuff where the inlines actually help you, or reified types. But otherwise, inlines have absolutely no impact on performance. Okay, back. Okay, maybe these slides were actually before. Anyway, these are the explanation how to capture. So if you are a girl, let's say, if you are in the, if you are the black one, and you put a stone in where it's called A, you can hit the white. If you are white and put the stone here, you can hit the black. So it's there is a lot of like a problem. And yeah, these are a bit of definition. Each one is a stone. A set of stones is called a string, and the liberties are the empty. So for example, this black block has 2 liberties. This was has a lot, so you don't even have to count. This has only 2. This has 2, and a lot of Go strategies based on the number of liberties. And then there is a group. For example, all the black stones here will do a group, which is very important when you study Go, as a human. But for the computer, there is no equivalent. It's very, very hard to define what is a group from the computer point of view, so we just avoid. We just talk about strings. And strings are touching, basically. Groups are connected, but not touching each other. Now, a strange problem with Go is when to decide who wins. Because, on chess, the last one wins. It's very easy. Instead, in Go, it's absolutely not easy to understand who wins. For a human player, what do? Basically, they count the territory that you are surrounding. So, for example, if this was a play, the black one will have the A part, this 2 in the C, and also the stuff of those D white, they are actually dead. Because from this position, there is no way that white can save those stones. I don't know if, because basically, whatever white can do here, if a black put 1 here and then 1 here, die will kill 2, and then black put another, white kill, and then black kill all of them. Because it's not the 2 eyes. Instead, these are 2 eyes, and this is alive. But when you have a player, human player, basically they can decide this is live, this is not alive. If there is some difference of opinion, you can keep playing until it's clear. But it's very, very hard to do an algorithm to be able to do this. So what a computer does is keep playing over and over again. Keep playing until all the left plays are only one side. One single empty space. Because then it's easy, because you never play where you have an empty space of your stones. Black cannot, if the X is black. Black will never play here. And white cannot play here because it will be suicide. There is no way that. And so when there is no place that you can play, you just quit. Then computer can just calculate calculate just the number of stones and the point that are surrounded on each stones. So, but it's strange because you have to keep playing much more than a human will do. So I will do very quickly. And so AlphaGo is the black and the white is the human. And this is how a professional game goes on. And there is a lot of strategy involved. And basically the strategy based more or less on that it's much easier to surround the territory on the corners. So first they play the corners, and then they play the lateral area, and finally the center. But on the other side, if someone get, for example, here, black is taking basically the territory here, but the white is getting the territory on center. So there is always a bit of take and give. Very, of course, I don't even pretend to understand exactly. I mean, there is a lot of, but it's very cool. At this point, I mean, even for a human player that is not professional, it's very hard at this point to understand who is ahead. But in this point, the world champion basically resigned because it was irremediably behind. Maybe something that, for example, those 3 stones are actually dead because you can see that there is no way that they can form 2 eyes. So they are already counted as white. And this instead are alive because here white has enough space to do 2 eyes. So this is a lot of stuff that stronger players do automatically, not even think about. And this, for example, these stones are actually connected because these shapes, I mean, if a white play here, black play here, so you can connect. So there is a lot of stuff going on. And so, but this is the the full board. When you play with someone else, basically, you can. Okay. I don't know. Are you a bit interested on this stuff, or let's see the code? Just another bit. Basically, this is one of it's called Tesuji. So this kind of a strange combination. Basically, here the black stones seems completely alive because you think, okay, these are the white. The white have only 1 eye. The black are here, and they are not far from here. So white is in a bad situation. But actually, these stones can be. There is a sequence basically where white put the stones here, and then black basically wanted to eat this one. He cannot place here because otherwise white eat these 2, so black will place here, then white extend. At this point, black cannot put here because otherwise it will be eaten, so black put here, and white put here, and put the trap. And then black doesn't realize that there is a trap, so eat the white. White play again, black eat again. And now white do this. At this point, these 3 are on peril, so black have to put here. And black does hit this one. And basically now, black is completely dead. Whatever it does, basically, white can play here, black can try here, and then black. It's completely black. This is how basically you develop your strategy. There's a lot, and the rules are so easy. But just for the beginners, basically, what you want is to play on something simpler. And you play on 9. The full board is 19 by 19. Instead, you play with the small one, 9 by 9. It's easier, and the matches are much shorter. So just to show you, basically, this is my software. So this is regulated one move for 10 seconds. So basically one black here, the white will be the software. And with one move for 10 seconds, I can more or less beat it quite regularly. But with the one move of 20, 30 seconds, it beat me. So it's kind of, I wrote a program that is stronger than me. That's already. And so basically, this is more or less what it will look like. It's not a great move. But it's not completely random. It's and if I give him like 30 seconds per move, the move started to be quite good. And okay, we don't have time, but it's quite easy. Okay, let's do the how algorithm to play games works. The easiest is the minimax. So it's basically take the current situation, you do some evaluation, who is ahead. Well, not at the beginning. At the beginning, there is no evaluation. So it take all the possible moves, and then it take the possible move of all possible moves, so it create a tree of all the moves. Then at the end, it evaluate the moves, and then it choose according to to who is the player. So here we'll take the lowest one, because of course it's your opponent, so we'll choose the best for him. And then you took the highest of the possibility of this level, and then you took the lowest. So each level you took either the highest or the lowest score. And at the end you have, because you assume that your opponent is playing the best for himself, and you're the best for yourself. And this is the first possible algorithm. And there is a problem that you have to expand all the moves, and in Go you have, but even in chess there are too many moves. So a possible, I mean, a better solution is trying to look at the moves, at the better moves first, and if you already have a move that is better, you basically prune the tree that is. So basically, if you already established that there is a move where he can kill you, it's pointless to look at all the possible response, because you already know that he has a better move than this. So in this way, you can cut a lot of moves in the evaluation. But this is still not enough for Go. And basically, the Go program uses this Monte Carlo tree search algorithm. Because the problem with Go is that at some point you wanted to evaluate. And for example, in chess or in other games, it's quite easy to evaluate. I mean, you have some heuristics, so you can count the number of pieces and stuff like that. But in Go, it's absolutely not easy, especially, I mean, not even professional can say at the beginning who is ahead. So what the program is doing some a rollout, so a completely random game. So it just put in a piece in a random place, only legal moves, of course. And the idea is that from a given configuration, plain random, statistically, the best position will win. I mean, the player with the best position. So if you do 10 times, it doesn't really matter. But if you do 10,000 or 100 times rollout, you understand who is actually winning that position. So and this is how basically you select the mover, you try to select the mover more promising, and then you do evaluation. And then you have to balance between discovering new moves or getting better evaluation for the moves that are kind of winning. Because maybe they are just winning. It seems they win, but just because of statistical fluke. So you have to run and run again. And so when you write a software to play Go, the most important part is how fast you can evaluate this rollout. And this is on my laptop, so nothing particularly fancy. And the first line was basically when I just take the Python code and copy paste it and translate it in Kotlin. It was let's just look at the first, or just the second, just one column. The first column is on the 9 by 9, the second column 19 by 19. In time in milliseconds to do a single rollout. And you have to think that you need at least 10,000 rollouts to make something work. And so the beginning was taking 10 milliseconds on the small board. So that will be like 100 seconds to have, more than 1 minute just to have a decent play. And then basically I keep improving, and the current, the last situation is basically 20 times faster, more or less, more than. And well, most of lesson learned on this performance stuff is that what is really important is the algorithm. So trying to avoid, for example, using immutable Go strings instead of mutable ones really help a lot of performance. Using a neighbor map, so instead of I just have a map with everything that can be pre-calculated. In this case, it was all the neighbor from each point. Instead of calculate every time you put in the map, so it really helps. To understand if a position is high, okay, I improve the algorithm. And this was quite, so for example, at the beginning, the random bot, so the one that do this random, was calculating all the possible moves, valid moves, and then just pick up one random. Instead, now basically it pick up random, then it check if it's valid, and if it's not valid, it pick up another random. But this is much faster than calculating all the valid and then pick up one random. And then, okay, instead of shuffle all the possible moves, just do the single swap and then do the random one by one, basically. Oh, if you can look at the code, everything is in Git. So, the last one is also quite nice. Basically, sometimes we are using map, like a hash map, but we actually, for example, I had the map with player 1 and player 2. So there was a map with the key player 1 and some stuff, key player 2 and some other stuff. But actually using an array is much easier, faster, because if the map is completely filled, because we completely put all the stuff and we know exactly where to go, using an array is much more natural. And I mean, coming from a Java world, arrays are kind of bad, because they are low level and we want map. But actually, also with Kotlin, it's much easier to use an array than with Java. And for example, one advantage is that if you go on an array, you don't have to put the double exclamation mark, because array always return. Instead, the map always return a nullable. And this was also helping a lot. And I don't know, I can show you some code. Well, let's talk about the next step. So at the moment, the algorithm is pretty good. It's already able to connect with the client, so you can play with it with a kind of decent graphic. Okay, there is something. The number that we saw was for a single core, for a single thread. Now I'm working on taking advantage of the full threaded. That is a bit difficult, but also Kotlin helps with coroutines and actor. It's really nice, the code. And once I finish this, basically the next step is using deep learning. And the point of deep learning in Go here is to basically when we do this Monte Carlo calculation, we have to trial the possible position. So in the middle and end game, that's quite good. But at the beginning, it's quite hopeless because you cannot really try truly all the possible 400 position at the beginning. And instead, what deep learning help you is doing a lot of analyzing a lot of games. It uses this kind of a convolution. So basically, it has a big net that take all the possible, and then it's split in small grid, smaller grid. And at the end, basically, it gives you the full, basically, a list of output which has the same number of the possible position on the board, with the position, basically with the probability for each one. So it can tell you which, it's kind of intuition. Analyzing the shape is understand the most good shape can be this, this, and this. I mean, the position where I could maybe play. And so you have a small number of a position, which are interesting, and then you can feed those to the Monte Carlo research at the beginning. So Monte Carlo research got a lot of improvement from this, because it doesn't have to, I mean, it started with a very good approximation. And then, of course, to have the final number, you have actually to verify that it works. But it's incredibly boost of performance. So this is, I think, after second half of this year, I will concentrate on this part of. I hope.